Chemistry is the science of how matter interacts. It starts with the atomic structure of the elements and how combinations of atoms form molecules. It includes the study of chemical reactions and their resulting electrical and chemical properties. In the 20th century, biochemistry, organic chemistry, medical chemistry, and applied chemistry have created much of the material basis of modern life. In core chemistry, the major chemistry disciplines are presented in a logical order, each building on the former. All matter, solids, liquids, and gases, is made up of a finite number of elements, or combination of these elements. To the chagrin of the medieval alchemist, it is not possible to turn one element, say iron, into another element, gold. What is possible is to form new combinations of the elements, or take apart existing ones. This is the art and science of chemistry. The science part was not possible until the atomic structure of matter was understood. But the art goes back to the time of early man. The first chemical reaction produced by humans started with wood, the trunks and branches of trees. Wood is made up of cellulose formed from carbon, hydrogen, and oxygen atoms. It is in fact known today as a hydrocarbon. This first man-made chemical reaction probably took place quite by accident. Indeed, all early chemical discoveries were undoubtedly lucky accidents. Fire is a naturally occurring chemical event. It is the oxidizing of combustible materials, such as trees and grasses. At some point, human groups everywhere learned to control and produce fire for warmth and the cooking of foods. Then, next, as must have happened many times, some wood, sitting next to a fire, underwent a chemical reaction. The heat caused the chemical bonds that hold the carbon, hydrogen, and oxygen together in the cellulose to break apart. As a result, the hydrogen and oxygen escaped, leaving behind pure carbon, known by the common name charcoal. It is a process that cannot be reversed. Charcoal is found in association with the earliest tools made by humans over 2 million years ago. Early man must have known that charcoal burns with a much hotter flame than wood. Charcoal played the primary role in the next great piece of ancient chemistry. Most metals occur naturally, not in pure form, such as gold, but as an ore, that is, in combination with other elements, particularly as oxides. One of the most important of these oxides for the development of human civilization was iron ore, that is, iron oxides. At around 3500 BC, ancient people in the Middle East found that by heating iron ores with charcoal, they could separate the oxygen from the iron through a chemical reaction that produced the gas carbon monoxide and pure iron. By 1500 BC, this brilliant piece of chemistry had fueled the beginnings of an iron-steel industry that has changed little in principle since those early times. Another great piece of ancient chemistry occurred again in the Middle East, also around 3500 BC, when metalsmiths learned that by heating the base metals of copper and tin, they could produce a whole new material. That material was bronze. This new alloy was stronger than either copper or tin from which it was made. The result was the production of a whole new collection of tools and weapons that fueled the rise of the ancient civilizations of the Mediterranean and Europe. that was only replaced by the introduction of iron weapons around 1500 BC. Another major chemical discovery of the ancient world was made by the Chinese around 200 AD. At first, this chemical discovery did not produce a new valuable substance, but an effect: fireworks. The chemical basis of this effect was a chemical reaction that took three naturally occurring substances, sulfur, carbon, and saltpeter, or potassium nitrate, mixed them together in precise proportions, and then ignited them with fire. The result was an explosion, a sudden expansion of gases created by the chemical reaction. What the Chinese had invented was gunpowder. Gunpowder was later found to produce an explosion that was powerful enough to propel a projectile, but did not blow up the gun or the cannon when the powder ignited. The resulting explosives industry has continued to expand even into the 21st century, and during its development has changed warfare and certainly human civilization more than any other chemical process. The Greeks, the Romans, and other great Mediterranean civilizations knew that if they could only understand the true nature of matter, a whole new world of wealth and possibilities lay at their doorstep. However, with the erroneous separation of matter into only four elements, earth, fire, air, and water, they were conceptually blocked from opening that door. It would take until the 1661 publication of Robert Boyle's The Skeptical Chemist to open that door. Electricity and simple water would come together in two experiments performed in 1800 that would lead to the greatest advance in technology the world would ever see. First, Italian Luigi Galvani made the chance observation that a charge from an electric machine could make the leg of a dead frog contract. He went on to show that connecting two dissimilar metals could produce the same contraction. He called this phenomenon animal electricity. Next, another Italian, Volta, made one of the great intuitive deductions in science. He reasoned it was not the animal that was producing the electricity, but the arrangement of metals and moisture. In 1800, he built the Voltaic Pile. In short, he built the first battery. He put together a little pile of discs, sequencing silver, zinc, and wet paper. On the top was zinc, and the bottom silver. By connecting wires to the top and bottom of his pile, he produced the first electrical flow, the first man-made electric current. In the same year, hearing of Volta's invention, William Nicholson, an English chemist, built his own primitive battery and immersed the two leads into water. Bubbles of gas rose to the surface. What was going on? By this means, later called electrolysis, Nicholson had actually decomposed water into its atomic components, hydrogen and oxygen. Oxygen appeared at one pole of the stack, the positive, and hydrogen at the other, the negative. Nicholson was in fact the first to perform electrolysis and the first to demonstrate that an electric current could produce a chemical reaction. From that moment, while still a mysterious phenomenon, electricity as a current would go on to power all the technological advances of the modern world. As for electrolysis itself, it would be used to separate many chemicals into their constituent parts. In the 20th century, the greatest technological impact of electrolysis would come in the form of the final step in the extraction of aluminum from bauxite ore. Ironically, 200 years after the first experiment in electrochemistry, the reverse process the joining of hydrogen and oxygen to form water, is the greatest hope for a new form of clean energy. It's called the fuel cell. From the time of the Greeks and Aristotle, natural philosophers believed that all things were made up of four basic elements: earth, fire, air, and water. It was called the phlogiston theory of matter. It was a limiting belief held until the mid-17th century, when Robert Boyle, often called the founder of modern chemistry, began to question its validity. What drove the chemists, or some would say the alchemists, for hundreds of years was the search for the philosopher's stone, a mysterious substance that supposedly turned base elements into gold, cured all disease, restored youth, and granted immortality. While not abandoning the alchemists' search to transmute metals, Boyle challenged the long-held assumption that every substance had to contain at least a small amount of the phlogiston's theory's four basic elements. He did this in a publication, The Skeptical Chemist. In publicly presenting his experiments, he broke with the tradition of secrecy maintained by the alchemists. This dramatic shift began the open exchange of ideas in science, the hallmark and even ethic of modern science. A century later, the scientific method, experimentation, observation, and publication, had supplanted the clandestine tinkering of the alchemist. As a result, the 18th century became the heyday of using heat to produce chemical reactions, as well as the study of gases. Particularly under assault were two of the phlogiston's theory's basic elements, fire and water. What were they really? The idea of water as a primary element was so strongly embedded in people's minds that many people thought it heretical when scientists demonstrated it was merely a false assumption. Water cannot be an element if it is made up of something else. By 1784, chemists such as Joseph Priestley, Antoine Lavoisier, and Henry Cavendish had shown in a series of experiments and demonstrations that water was, in fact, not a fundamental element. Water was actually made up of oxygen and hydrogen. Not only had they separated water into oxygen and hydrogen, but they also reversed the process using oxygen and hydrogen to produce water. In one such ingenious experiment, Priestley used a magnifying lens to heat mercuric oxide, which gave off pure oxygen. He trapped it in the glass container that housed the experiment. Now, with ample oxygen to play with, Priestley and others quickly learned that this gas could enhance the burning of a candle and other combustions. The old phlogiston theory was collapsing, but what would replace it? By the turn of the century, electrolysis of water had allowed scientists to simultaneously capture both hydrogen and oxygen. One of the intriguing questions that resulted from these experiments was, why was there always twice as much hydrogen as oxygen? And why was carbon dioxide, another gas given off by fermentation, always made up of the same proportions of carbon and oxygen? The answer came in 1808, when John Dalton published his new system of chemical philosophy. In it, he proposed that matter was made of atoms, tiny invisible spherical bodies of fixed masses. Some of his elements were hydrogen, carbon, sulfur, iron, silver, and gold. But unlike earlier atomists, he assigned a specific weight to each of his elements. This was the conceptual revolution all chemistry was waiting for, and would lead to the periodic table 60 years later. although some of Dalton's elements were in fact compounds and his nomenclature was never accepted. This new idea of matter spread like wildfire. The atomic nature of matter set the stage for all the great discoveries of the 20th century, and eventually to the release of energy from the atom itself. In 1808, when Baron Johannes Jacob Berzelius coined the term organic chemistry for the study of compounds derived from biological sources, the atomic theory of matter was well on its way towards universal acceptance among chemists. However, at that time it appeared biological matter from plants and animals was fundamentally different than non-organic material, rocks, minerals, gases, and liquids such as water. The idea was that organic compounds contained something scientists called a vital life force. Part of this idea was that life substances, such as blood and urine, could only be formed in the body of a living organism. Then in 1828, a German chemist, Friedrich Wöhler, told Berzelius, "I can prepare urea, urine, without requiring kidneys or animal, either man or dog." In that moment, when Wöhler synthesized an organic compound, he debunked the vital life force theory and launched one of the most productive branches of modern chemistry, organic chemistry.
The goal of the process is to get mitochondrial and chloroplast DNA from tissue like this, is to grind it up and extract the DNA.
By the 20th century, organic chemistry was defined as the study of carbon compounds from both biological and non-biological sources. Soon, organic chemists were no longer satisfied with duplicating nature's work, but started developing and designing new organic compounds. It began during World War I, when, in the process of looking for a synthetic replacement for rubber, chemists discovered how organic compounds were put together. What they found was that many were made of simple molecules repeated in long strands called polymers. The search was now on to find synthetic replacements for natural materials used by industry. Successes were spurred by World War II. Silk, a natural fiber made from the cocoons of caterpillars called silkworms, was found to be made of simple molecules repeated in long strands. In 1935, DuPont Labs produced a silk-like synthetic polymer made primarily from coal. When they took the gooey, coal-based substance and pulled it out into a long strand, what they had was a synthetic fiber called nylon. An inexpensive replacement for silk. It was an instant hit with women who started wearing nylon stockings. Soon polymer science had become a whole new branch of chemistry, leading to the modern wonders of plastics. The manufacture of plastics based on petrochemicals is a major industry in the United States and the world's economies. Some of the better known plastics are polyurethanes, used in the making of plastic containers, plexiglass, toys, and utensils. Styrofoam, used for packing and insulation. And polyester fibers, used in clothing. By the mid-19th century, the number of identifiable elements had grown to over 50, enough to stock a chemistry lab and enough to look for ways to organize them. At that time, it was known that each element had the possibility to exist in 3 states: a gaseous state, such as oxygen and hydrogen, a liquid state, such as mercury, or solids, such as copper. But was there any other order to them? In 1869, Russian chemist Dmitry Ivanovich Mendeleev made a startling discovery. He wrote the symbols for the 65 known elements on cards with their atomic weights. On a cold winter night, he shuffled them around, finally putting them in columns and rows showing similar chemical properties. What he found was an underlying pattern, a repetition of properties. Mendeleev discovered what is now called the periodic table of elements. However, his table had gaps. Mendeleev was so confident in his discovery that he not only predicted these missing elements would be found, but also what their properties would be. Time proved him correct. In the decades since he developed his periodic table of the elements, scientists around the world raced to be the first to discover new elements and fill in his chart. There are now 9 basic element groups: alkali metals, alkaline earth metals, transition metals, other metals, metalloids, nonmetals, halogens, noble gases, and rare earth elements. To see commonalities within each group, take the nonmetal group, for example, which contains some of the most important elements for life: hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, selenium. This piece of coal, carbon, is typical of the group. It is brittle and cannot be made into a wire. In fact, all the elements in this group cannot conduct electricity, and they do not reflect light like a metal does. On the other hand, the transition metals form a large group of elements. Using copper as an example, they are all ductile and malleable. They all conduct electricity and heat. Interestingly, the group also contains the only elements that produce a magnetic field: iron, cobalt, and nickel. Finally, the noble gases. Typified by neon, which lights the urban night, are all highly stable, rarely interacting with other elements. Understanding why there is this periodicity of elements would have to wait until the quantum mechanics solar system model of the atom was revealed at the beginning of the 20th century. However, by the 21st century, the number of elements had grown to over 110, with over 20 now being man-made at such high-tech facilities as Argonne Laboratory, Fermilab, Lawrence Livermore Laboratory, and Thomas Jefferson National Accelerator Facility. As for the periodic table, it has expanded and been revised a number of times, but Mendeleev's original pattern is still there, embedded in each new edition. With the detonation of the atomic bomb and the discovery of subatomic particles, the investigation into the fundamental nature of matter was now clearly in the realm of physics. After World War II, the focus for chemists was on understanding the properties of matter, the kinds of changes matter can undergo, chemical reactions, and the invention of new molecules. By now, it was well known that a couple of fundamental laws governed chemical reactions. The first was that reactions always moved from a higher energy state to a lower energy state. For example, when wood is burned, that is oxidized, the resulting carbon dioxide gases have less energy to do work than the original wood. In short, chemical reactions always follow the second law of thermodynamics, since they move toward maximum entropy, or the greatest state of disorder. Fortunately, for us here on Earth, another law states that chemical reactions in nature proceed slowly. Oxidation of iron or paper usually proceeds at a slow pace. 1,000 years ago, medieval alchemists had learned that most chemical processes could be sped up by applying heat, as when a magnifying glass intensifies the sun's heat on a piece of paper. This new factor, heat, is called a catalyst. Catalysts can speed up the rate of chemical reactions without being used up or changed themselves. Physical chemist Dr. Scott Cowley demonstrates how a catalyst works.
I'm going to demonstrate the principle of catalysis. I have in this test tube a 30% hydrogen peroxide solution, and that hydrogen peroxide solution is undergoing a decomposition thermally. As molecules collide, they decompose in the following way, in which hydrogen peroxide, H2O2, falls apart or decomposes into water and oxygen. Now that's happening thermally here, but it's so slow you can't observe it. If I add a catalyst to this speeds up the process, and you can see bubbles now being generated, and that is because it's lowering the energy it takes to go from reactants to products. So a catalyst speeds up the reaction. In itself, it's not consumed, or it actually gets involved in the reaction, but it gets regenerated at the end. So you can see this is a platinum on aluminum oxide catalyst. This is something that would typically be used in a platinum reformer in a petroleum refining operation to make gasoline, high-octane gasoline. At the Colorado School of Mines, we've also developed a catalyst which we call a Nano Catalyst. It's much higher activity, and you can see that because of the very small particle sizes, this particular catalyst will also undergo a reaction. You can hear the popping sound as this is generating oxygen so fast that it actually is blowing the particle apart. It's over-pressurizing the pores, and we end up with a much faster reaction taking place, and you can see that this is obviously happening much faster than the first case.
Finding new catalysts, including biocatalysts called enzymes, accelerated after World War II. For example, converting corn to ethanol was easy, but converting any biomass to ethanol is a problem of finding new enzymes. Biochemist Andy Aiden is researching the second aspect of the ethanol challenge.
The second aspect is getting the enzymes that can break down these cellulose molecules of the biomass into the sugars themselves. Just breaking down that biomass, it's a tightly woven matrix of material. We have to break that apart efficiently, convert it to sugars, and then ferment those sugars.
Indeed, without accelerating nature's naturally slow chemical reactions, the chemical industry would not be able to function. The result? An explosion in the invention of new chemicals. Today, over 1 million new chemicals are produced each year. In fact, the chemical industry accounts for over 30% of America's total industrial output. Areas of growth include the chemical energy industry, the pharmaceutical industry, the biochemical industry, chemical engineering, and agricultural chemistry. There is no end in sight to what might be possible through new chemical processes and molecules.